Hey everybody, it's Ms. Phoebus, and I'm back with another lesson, lesson 53, geometric sequences. This builds off of what we talked about yesterday with our arithmetic sequences and then those patterns that we looked at, Fibonacci and all that stuff. So we're looking at geometric sequences today. And we're going to hit three skills. I can recognize geometric sequences, can be expressed by exponential functions. I can determine an explicit formula given a geometric sequence, and I can write a recursive formula given a geometric sequence. So if you're having trouble with the arithmetic, you definitely need to stop in for a Google Meet so I can help you out with that, because we're going to do a geometric one as well. All right, and then here's our standard construct linear and exponential functions. That's what we're going to focus on today, including arithmetic and geometric sequences given a graph, a table, a description of a relationship, or input-output pairs. And we're going to go more into that different style of stuff next week. We're going to be on page 263 in the notes. We are going to jump because we did cover some arithmetic sequences in between the geometric stuff. So there will be a jumping point at some point later on in the lesson.
Geometric sequences have a constant ratio from one term to the next. So we've looked at you're either multiplying or dividing by the same number, and that's called a common ratio. And in this case, we're multiplying by 2 each time. Now, the common ratio is something that can be a little bit more difficult to find versus the common difference. And so you can always find the common ratio if you take the second number and divide it by the first number, or you could take 880 and divide it by 440. That would get you 2 as your common ratio in this example. So the common difference you subtract. In this common ratio, you end up dividing. So that's what ratio is being used there. If you have difficulty telling what it is, that's how you can figure out what you are multiplying or dividing by. Now, when we talk about division, you will not use divide, like the division symbol. You're going to be writing things as fractions or decimals. Geometric sequences are modeled by exponential functions. So we're going to get into what an exponential function looks like and all of that stuff. You've kind of seen them before, but we're going to get more in depth as we go through this unit. All right, the explicit rule for a geometric sequence has its own formula base, and we've got this a sub n pop up. We know that the a sub n is the nth term, so that n can stand for any number. And so it could be 22nd term, 105th term, a millionth term. We've got all kinds of numbers that we could plug in here. But right now, it's just going to be the nth term. Equals a sub 1 is the first term, just like in our just like in our arithmetic sequences. And then r is going to be your common ratio, what you're multiplying or dividing by. N is in this parentheses set still. It doesn't need parentheses, but it's still grouped with this -1. Remember, with arithmetic, it was n minus 1 after your common difference. So it's still grouped there, but it's up in the exponent. So all of this is in the exponent. So you need to write up and to the right of your r value. N still represents the position number, and it will probably remain a variable for most of the time unless you are actually plugging in a number to figure out what number's in that spot. Geometric sequences can only be simplified if you have the same bases. So a sub 1 and r, if they are the same number, you can simplify. Otherwise, you're not allowed to simplify. So a lot of people try to multiply these together. Don't do it. Don't ever do it. Never, ever do it. Don't multiply those together. That's like a big no-no. Okay, I'll show you. If you can simplify it, I will show you what it looks like, and I will show you how to do it. Okay, I promise. All right, so let's look at some examples. So we've got 1.5, 3, 6, and 12. So we're going to look at our rule. Looks like we're multiplying by 2 each time, and multiplying is, of course, geometric. We still have our term values. Looks like I have the first, second, third, and fourth. We'll go ahead and fill out the fifth. And so our first term is 1.5, the second is 3, the third is 6, the fourth is 12, and then the fifth ends up being 24 because 12 times 2 is 24. Now here I didn't really scale this out but each of these lines is going to represent 1. So I want you to think about this as like quadrant 1. And so 0, 0 is in the, I know you can't see it, but you can probably see on your page, 0, 0 is down here. And so this would be 1, 2, 3, 4, 5. And then we would be counting, we have 5, 10, 15, 20 that we can reach, which we can't quite get 24 on there, but we'll get as many as we can. Okay, there's 1, 1.5, 2, 3, 3, 6, 4, 12, and 5 doesn't fit on there. 5.4 doesn't fit on there. But if you notice, I can't connect these with like a straight line. I don't want to connect them with anything right now, but it's definitely a curve. You see that? Definitely a curve. So that's why we have to model it with something that's not necessarily linear. We're going to go with exponential. So this is still a discrete function, so don't connect the dots. This is not an arithmetic function because it's not linear. It's growing by a constant factor. I'm multiplying by the same number each time. So therefore, this geometric sequence is best modeled by an exponential function. Its growth is growing. Okay, let's look at example 2. Okay, I have 18, 9, 4.5. So it looks like especially if I take 9 and divide it by 18, 9 divided by 18 is 1/2. So I'm dividing by 2 each time. That is geometric, or you could say I'm multiplying by 1/2. I'm still going to try to get 5 numbers on there. So I've got 18, 9, and 4.5. To get the next number, I'm going to divide 4.5 by 2 or multiply by 1/2 and get 2.25. And to get the next number, I'm going to divide that by 2 and get 1.125. All right, so let's graph this. So 118, 2, 9, 3, 4.5, 4, 2 and a smidge, right? 2.25, and then 5, 1.125. So just a little bit above 1. So definitely a curve, definitely not a straight line. So we aren't going to connect them. It's still going to be discrete, but it's geometric and it's modeled by an exponential function. So definitely a curve there. All right, here we go. Example 3, 20, 15, 11.25. This one might be a little bit tougher to figure out the rule. So again, we know that we're probably multiplying or dividing here. So we can take the second number and divide it by the first numbers. 15 divided by 20 reduces to 3/4. So we're multiplying by 3/4. So if I continue that pattern, I'm going to have 2 numbers. Now, here we can round. I'm all right with that, but definitely give me a couple decimal places. And so here's the graph there. Now, some of you might argue that it does look pretty linear. It curves just a little bit kind of there at the end. And that's because 3/4 is really close to 1. If I'm multiplying by 1, I'm actually not going to be changing the numbers in my sequence. So anytime we get something just on either side of 1, if I'm multiplying by 0.9 or if I'm multiplying by 1.1, it's going to look very close to being linear, but it is going to be modeled by an exponential function. The curve is just not going to be as noticeable. All right, so it's still discrete, it's still geometric, and it's an exponential function. All right, let's figure out the common ratio. I've already talked about it a little bit, but here are some more examples of figuring out what the common ratio is. And remember that you're going to take the second number and divide it by the first number. So in this case, you might be able to tell that you're multiplying by 4 each time, but if you're stuck, you can always take 8 and divide it by 2. 8 divided by 2 is 4, so the common ratio is 4. All right, number 5, the second number divided by the first number. So if I do 1920 divided by 7,680, I get 1/4. Now, if you wanted to use 0.25, you could, but 1/4 is perfectly fine answer as well. All right, so if you're multiplying, R will be a number larger than 1. So if you are multiplying and you can tell my number is getting bigger and bigger and bigger, you're multiplying by a number bigger than 1. If you're dividing, R is going to be a number between 0 and 1, and that's where that fraction idea comes in. So if I've got 0.5, 0.75, and 1.125, I can take the second number and divide it by the first number. 0.75 divided by 0.5 is 1 1/2, or 3/2. So I really think that second number divided by the first number is key. It's definitely, especially if the common ratio is weird. So you might want to make sure that you have that highlighted or written down or starred or something so it stands out to you in the notes. All right, number 7 and 8, we're going to write the explicit rule, but we have a little bit more work ahead of us than 9, 10, and 11. 9, 10, and 11, they pretty much give you everything that you need. 7 and 8, you have to figure out the first term and the common ratio. So here I've got all set up. I'm just going to replace a sub 1 with the first term and r with common ratio, and then we'll be done writing the explicit rule. So a sub n equals my first term, my first term in number 7 is 3. So I'm going to replace that a sub 1 with 3. And then I have to figure out what I'm multiplying by. So I've got 3, 9, 27, 81. If I'm having trouble, I can do 9 divided by 3. 9 divided by 3 is 3. I'm multiplying by 3 each time. So I'm going to replace that r with 3. Now, because this 3 and this 3 are the same number, I'm going to be able to simplify, but I don't want to do that quite yet, okay? But definitely do not multiply these 3's together. You are not allowed to simplify these by doing the multiplication of a sub 1 and r. I will show you some examples where you can simplify and you don't even multiply in those examples, so just don't do it. Like, really don't do it. All right, let's look at number 8. The first term is 85, so I'm going to replace a sub 1 with 85. And then here I might have some difficulty, so if I take negative 17 and divide it by 85, I get negative 1/5. Now, this is a rule of thumb just to kind of help you notation-wise. If your r is negative, you definitely want to wrap it in parentheses. So go ahead and make sure that you wrap that negative 1/5 in parentheses, because you don't want that negative to escape and make it look like 85 minus 1/5 to the n minus 1. So you want to wrap all of that in parentheses and make sure that that negative kind of stays in with the 1/5 and know that you are multiplying those together. Now you definitely need a multiplication symbol, or you could even wrap 3 here in parentheses, but you have to know that those are two separate numbers and it doesn't become just a 33 to the n minus 1. It's 3 times 3 to the n minus 1. All right, number 9, we're going to plug in 13 for a sub 1. We're going to plug in 5 for r. And there we go. We've got the explicit rule. For number 10, we're going to plug in 8 for a sub 1. We're going to plug in negative 11 for r, but we're going to make sure we wrap that in parentheses to keep that negative together with the 11 so we don't lose it. All right, number 11, a sub 1 equals 0.5. So we're plugging in 0.5 for a sub 1, and we're plugging in 3.5 for r. Again, remember, we're not allowed to multiply these together, so just leave them, show the multiplication in between them, but don't multiply them together. All right, let's look at simplifying now. You can simplify some of the geometric rules. You're only going to be able to simplify right now if you have the same bases. So remember that if we have the same bases, we add the exponents. So remember how we had x squared and x to the third, and we wanted to multiply them, so we added the exponents together and we got x to the fifth. The same thing happens in these examples. So I've got 2 as a base, I've got 2 as a base, I'm going to be able to add their exponents. I've got 1/3 as a base, 1/3 as a base, I'm going to add their exponents. So remember that 2 is just 2 to the first, and this is 2 to the n minus 1, so I'm going to write 2 to the, and I'm going to add their exponents, 1 plus n minus 1. Now I have a positive 1, and I'm adding a negative 1, and 1 plus negative 1 cancels, right? And so I'm left with a sub n equals 2 to the n. So you can only do this if the bases are the same, and you are adding the exponents. You're not even multiplying. So let's look at 13. We've got 1/3 to the first and 1/3 to the n minus 1. Because the bases are the same, I can add their exponents. I'm going to add the 1 and the n minus 1. And then this 1 and the negative 1 cancel each other out, but I still have that in there. So this is 1/3 to the n. So it's a different way to write a geometric rule, but when you're writing your explicit rule, I expect you to have this n-1 there. You probably aren't going to be doing a whole lot of simplifying or being asked to simplify with the geometric rules. With the arithmetic, that'll probably happen. All right, let's look at using some of these. So we've got a geometric sequence. It's a sub n equals 5 times 2.5 to the n-1. Now, if you are using a graphing calculator or a graphing calculator app, you can shove the whole entire thing into the graphing calculator, hit enter, and get the right answer. But if you have a different calculator where you have to do it step at a time, you need to make sure that you are following the order of operations. So you're going to do the subtraction and the exponent after you plug in a number for n. Then you do use that exponent. So we'll do 2.5 to some power, and then you multiply times a sub 1. Okay, so multiplying is fast, is last. You've got to deal with the exponent a whole lot more, and exponents in order of operations, remember PEMDAS, exponents are up near the front. So we're going to find the sixth term, so that means that we're going to plug in 6. So I've got 5 times 2.5 to the 6 minus 1. 6 minus 1 is 5. And so what you need to do, because I kind of ran out of room here, you would do 2.5 to the 5th power, and then whatever that answer is, multiply it by 5. And so you should get 488.28. All right. If you have a graphing calculator, you can just shove this whole entire thing in, and the graphing calculator will obey the order of operations. The 10th term, you're going to plug in 10. You're going to do 10 minus 1 and get 9. So you're dealing with 5 times 2.5 to the 9th power, which ends up being 19,073.49. Now, these numbers get really big really fast. I'm probably not going to ask you to plug in 100 and find the 100th term, because that number is going to be huge. We're going to see when we do number 16 that when you plug in 21, you're going to get a ginormous number. So I'm going to keep those relatively small. So just keep that in mind. So when we plug in 21, we do 21 minus 1. That's where the 20 comes from. And then 2.5 to the 20th, and whatever that answer is, multiplied by 5, and you should get 454,747,350.9. That's a big number, okay? And if we go to the next number out, it's going to be even bigger. So that's why we're probably not going to go way far out there. We're going to keep it kind of close. Single digits, maybe some teens, maybe low 20s, but not going to ask you to go too far out there. All right, a sub 13, we're going to plug in a 13. 13 minus 1 is 12, so we got to figure out what 2.5 to the 12th power is, multiply that by 5, and then we get 298,023.22. So the recursive rule, just like for our arithmetic one, has two equations. The first one is going to be about the first term, and then the second one includes the common ratio. So the difference here between what we were working with the arithmetic one is that we now have this r, the common ratio, involved. So a sub 1 equals a number. That's going to be the same as our arithmetic. A sub n equals, and we've got a sub n minus 1. That's going to be the same thing, except now we've got to make sure that we have this multiplication, and r, our common ratio, is involved. So we're going to find the first 5 terms of the sequence, in which a sub 1 is 5 and a sub n equals 3 times a sub n minus 1. Again, remember that the hardest part of this is understanding the notation, understanding what this a sub n minus 1 means. So we're going to work a little bit more on that in this problem. So a sub 1 is 5. And why is that 5? Well, it's because they told us that the first number was 5. So because those are both 5s, we know what a sub 1 is. A sub 2, we're going to plug a 2 in for n here and n for this n over here. So we're going to end up with 3 times a sub 2 minus 1. And then we're going to simplify that 2 minus 1 down. So that's really going to be 3 times a sub 1. And a sub 1 is that 5 that we got in the last answer. So we're going to just pull down that 5, and 3 times 5 is 15. So the second term is 15. And yes, that 5 is the same as the very first 5 that we had. So our second term is 15, our first term is 5. All right, let's figure out our third term. So we have a 3 down here. So that's like putting a 3 in for n here. We're going to put a 3 in for this n over here. So we're going to have a sub 3 equals 3 times a sub 3 minus 1. You're having a hard time there probably seeing the minus. It shouldn't be minus. Why are these? Oh, no, that's right. Minus 3 minus 1, duh, is 2. So that's going to turn this into 3 times a sub 2. I was thinking, oh, we should be multiplying. But no, it's n minus 1. I don't know what happened there. All right, so 3 times a sub 2. Well, a sub 2 is that last number we found. A sub 2 equals 15. So 3 times 15 is 45. And yes, those 15s are the same 15s. You can use the number before, multiply by 3 to get the next number. All right, a sub 4 equals 3 times a sub 4 minus 1. So we're plugging in a 4 for our n's. And then we're going to simplify that 4 minus 1. That's 3 times a sub 3, sorry. And a sub 3 was that last number that we found. A sub 3 is 45. So we're going to have 3 times 45, and that's 135. And yes, those 45s are the same 45s. A sub 5 is going to be equal to 3 times a sub 5 minus 1. And so that 5 minus 1 is going to reduce down to a 4. So we've got 3 times a sub 4. And a sub 4 is that last number that we just found. So we really want to take 3 and multiply it by 135, and we get 405. So our sequence is, and yes, those are the same 135s. Our sequence is 5, 15, 45, 135, and 405. And we built that sequence by taking the first number and multiplying it and every number after it by 3 to get the next number. So that's the first 5 terms in our sequence. All right, so let's see if we can find the first 5 terms in this sequence, which starts with a sub 1 is negative 2. So we already know a sub 1 is negative 2. And to get the next number, we're going to plug in the number before. That's the a sub n minus 1. And we're going to multiply it times 4. So to get a sub 2, we're going to do 4 times the number before, which is negative 2. 4 times negative 2 is negative 8. To get the third term, we're going to do 4 times the number before. Well, the number before we just found was 8, negative 8, sorry. And so 4 times negative 8 is negative 32. To get the next number, we're going to do 4 times the number we just found. So 4 times negative 32, and we'll have negative 128. And then to get the fifth number, we'll do 4 times negative 128, and we'll get negative 512. So our sequence is negative 2, negative 8, negative 32, negative 128, negative 512. All right, the next one, the first 5 terms in the sequence, we already know the first one's 16 because they gave it to us. And then we're going to take that 16 and we're going to multiply it times 1/4 to build the next number. And then we'll multiply that times 1/4 and keep multiplying by a 4th. Okay? Technically, multiplying by a 4th, you're dividing by 4. So, same idea. So we're going to do 16 times a 4th. A 4th of 16 is 4. To get the next number, we're going to do 1/4 times 4. 1/4 times 4 is 1. To get the next number in the sequence, we'll do 1/4 times our answer. So 1/4 times 1 is 1/4. And to get the last number, or the fifth number in the sequence, we're going to do 1/4 times 1/4, and that's 1/16. So our sequence is 16, 4, 1, 1/4, 1/16. All right, let's do another one. The first 5 terms in the sequence, which a sub 1 equals negative 1/2, and a sub n equals 2 times a sub n minus 1. So these two problems are probably a good time to go ahead and pause it and see if you can figure out what the 5 terms are for 4 and 5. And then unpause the video when you're ready, and then you can check and see if you're right. All right, so a sub 1 on number 4 is going to be negative 1/2. and then we're going to just multiply each answer that we get from the problem above, or the number before, we're going to multiply by 2. So to get the second one, we're going to do 2 times negative 1/2, and we're going to get negative 1. And then the next one, we're going to do 2 times negative 1 and get negative 2. And the next one, we'll do 2 times negative 2 and get negative 4. And then we'll do 2 times negative 4 and get negative 8. So our sequence is negative 1/2, negative 1, negative 2, negative 4, negative 8. All right, example 5, our first term is going to be negative 27, and we're going to multiply each of those answers by 1/3 and then create our sequence that way. So 1/3 of negative 27 is negative 9, and 1/3 of negative 9 is negative 3, and 1/3 of negative 3 is negative 1, and 1/3 of negative 1 is negative 1/3. So our sequence is negative 27, negative 9, negative 3, negative 1, negative 1/3. Hopefully you did well. All right, let's use these tables to create a recursive rule that models the sequence. So a lot of times if they just give you a random table, you may have to first figure out if it is arithmetic or geometric. Since we're just talking about geometric right now, we can go ahead and assume that they're geometric, but that may be one thing that you have to figure out is it arithmetic, is it geometric before you start writing rules, because that's going to dictate what your formula is that you need to look at. All right, so we know that we need 2 terms, the first term, and we need to know the common ratio times a sub n minus 1. So we're filling in 2 pieces. So you can have this formula out when you go to write your rules, when you're working on a quiz or a test or something like that, and you're just really plugging in what a sub 1 is and what that common ratio is, and then you're done. So the first term is whatever's in the first position. So it looks like a sub 1 equals 0.16. And then we have to figure out what we're multiplying by. Our numbers are definitely getting larger, and it might be hard to tell down here, but remember, to find your common ratio, you take a second number and divide it by a first number. So a number on the right divided by the number just to its left. So 20 divided by 4 is 5. So our common ratio is 5. So in that spot where there's an R, we'll put in a 5. So a sub 1 equals 0.16. A sub n equals 5 times a sub n minus 1. And that's it. That's your equation. Recursive rule. I guess I should say equations, right? Because there's 2 of them. All right. So for the second table, a sub 1 equals, what number do you think? I'm thinking 1,000. A sub 1 equals 1,000. And let's try to figure out what we're multiplying by. Our numbers are getting bigger, so it's definitely going to be a number bigger than 1. Let's do 2,500 divided by 1,000. So that would mean that our R value is 2.5, or 5/2. So a sub n equals 2.5 times a sub n minus 1. That's, both of those together are a recursive rule. Remember, you need to know how the sequence is changing, but also where to start. So you need both pieces of those. All right, so explain in your own words, what is the difference between explicit and recursive rules? What do you think? Here's what I think. I think explicit rules are made up of only one equation. You can plug in the position number and find the number in the sequence. Pretty easy. That's the strength of an explicit rule. Recursive rules are made up of 2 equations. In order to find a particular number in the sequence, you must find all the numbers in the sequence. So depends on how far out you're going. If you're going not very far, recursive is probably the way to go, right? You have the first 3 terms. You need to find, the 7th term. You don't have to go too far. Why write an equation? Just continue the pattern. But an explicit rule is for when you have to go way on down the road. We don't want the 7th term. We want the 700th term. So that's where an explicit rule is strongest, is if you have to go way on far down the line. So they have their pros and cons, and and that's why you're kind of working with both of them. But you are really kind of worried about making sure you understand that notation, really what you're worried about. All right, so let's write a recursive rule to model the sequence and then find the 6th term. So looks like our first number is 16, so a sub 1 equals 16. This one might need to figure out, it's kind of hard to tell what you're multiplying by. You're definitely multiplying by a number bigger than 1. So we may take 56 and divide it by 16. 56 divided by 16 is 3.5, or I wrote it as 7 halves here. Doesn't matter which one. All right, and we want to find the 6th term. So I already have the first 4 terms. So I've just got to find the 5th term and then find the 6th term, and then I'll be done. So I'm going to figure out what the 5th term is by taking that 686 and multiplying it by 7 halves, or 3.5. And when I do that, I get 2,401. To get the 6th term, which is the one that I really want, I'm going to take that 2,401 and multiply it times 7 halves, and I'm going to get 8,403.5. And that is my answer there. All right, so here we're going to find the 11th term, so we're going to have to do a little bit more work. I think I talked about it in the last video. It's going to be a little bit more tedious, but it's not too terrible. It's just pretty much you typing the same thing in the calculator over and over again, right? So we're going to write a recursive rule to model the sequence. So we know a sub 1 is 32.4. And we know, well, it's kind of hard to tell what our common ratio is. So I'm going to stick in my calculator 18 and divide it by 32.4. And when I do that, I get 5/9. It's like 0.5 repeating. If you want to call it 0.56, you can. Definitely give a couple decimal places. The more places that you give, the more accurate your answer, right? You don't have a rounding error as much. We have the first 3 terms. So to get the 4th term, we're going to multiply that 10 times 5/9. Now I think I switch over to decimals here. So I'm going to try to give 2 decimal places if I have room. Well, that one I didn't have room. So 10 times 5/9 is 5.6. And I'm going to multiply that by 5/9. I guess I'm going to just stick with 1 decimal place and get 3.1. Multiply that by 5/9 and get 1.7. Multiply that by 5/9 and get 0.95. Multiply that by 5/9 and get 0.53. Multiply that by 5/9 and get 0.29. Multiply that by 5/9 and get 0.16. And here's my last one. Multiply that by 5/9 and get 0.09. So that's the number that I'm looking for. Again, I probably would want to do a lot of this in the calculator and save the rounding for the end, but I didn't have enough room for that. So this is what I did. So it's probably got a little bit error. It's off a little bit. Probably could write it a little bit nicer as a fraction, but this is perfectly fine. All right, so if you are having to find a specific position, like what number's in that position, you're going to have to build the sequence. And that's what we did here. I had to go all the way up to 6, or I had to go all the way up to the 11th term, and I had to find all the numbers in between. All right, so that's it. That's the end of this video.